Hello, I'm Dr. Burke. This is your interference lab video. I'm in my garage. Sorry about the delay on this video. We had trouble getting everything together in order to do it. So, anyways, we'll start by looking at a double slit interference situation. And this slide here, or this piece of paper I've drawn notes on, that the path length difference between the above slit and the below slit is d sine theta, where d is the distance between the slits. When that's equal to an integer times lambda, the wavelength, you get a bright spot. Now, the distance between the slits is going to be much smaller than the length, the throw distance to the screen where you'll be looking at it, and why there is the position of a bright spot there, say the mth bright spot. So in this situation, sine theta is nearly equal to tangent theta, and tangent theta is y over L. And so the position of the mth bright spot is going to be m lambda L over d, and the m plus first bright spot is m plus 1 lambda L over d. So the distance between bright spots on the screen is just going to be lambda L over d. Now you can use this equation to find if you know the slit width, distance between the slits d and lambda, then you could, or d and L, say, you can use delta y in order to determine lambda. Also, if you know, if you don't know the distance between the slits, but you know lambda and L, you can use the distance between bright spots to get the little d, the distance between the slits. A diffraction grating ends up giving you the same result. You could look at that in your textbook. So the distance between bright spots, delta y, on the screen is lambda L over d, where d is the distance between adjacent slits in the grating. So if you're given so many slits per millimeter, the inverse of that will be the distance between the slits in millimeters. So if you're given 500 slits per millimeter in a diffraction grating, the distance between adjacent slits is 1 over 500 millimeters, or 1/500th of a millimeter, okay? Which is, I think, 20 microns, but you can work that out. Now, single slit's a little different. This calculation, again, is done in your text. So if you just take the top of the slit and the middle of the slit, the path length difference is a over 2 sine theta. When that's equal to lambda over 2, you get a dark spot. So if you do that progressively through fractionations of the slit width, you'll get that a sine theta equal to m lambda is a dark spot, and a sine theta equal to m minus a half lambda is a bright spot, where m, like Mary, is an integer, 1, 2, 3, 4, 5. And then the distance between the bright spots for a single slit is this lambda L over A. And this is that calculation. Now, these calculations are all in your textbook, so I'm just doing them as a courtesy. But you're supposed to be seeing this in your text. So, double slit calculation, you can freeze the video and snapshot that. The next page of that calculation, the third page of that calculation, is the diffraction grating. And then the single slit. This is done in more detail in your textbook. And then the distance between bright spots and the single slit. So this is fine and dandy, and that's really just some geometry and some algebra. Now, we have here a Cadillac, and we have a laser of wavelength 550 nanometers. It's a green laser. If I'll shine it over the far wall, you'll be able to see the beam better now. See that beam? That beam goes over. It's going to hit that. You can see that bright spot there that's hitting. So if you look at this laser, you can see there's dust here in the garage, so you can see the laser light hitting the dust particles, which enables you to see the beam as it moves along here. And it's going to come in and smack this piece of wood here, which is basically an old dresser sitting in the garage here. So the first thing we'll look at is a diffraction grating, just because I have a diffraction grating here. I'll show it to you. This thing here, if you can look at it, whoops. Let me turn it right side up here. This is the slits are so close together you can't see them. It looks like a clear slide. But there's 500 lines per millimeter here. So the distance between the bright spots will be lambda L over D, where D will be 1/500th of a millimeter. So let me turn my laser like this. Let me put it at the edge here. I'll put it on the table. I have some rubber bands here holding the laser button on. And let me take so the distance L is going to be, in those formulas, is going to be the distance between the diffraction grating and the screen. The screen here is this Cadillac. So if I take this, there's the laser, and the beam is hitting the Cadillac right there. It's awful bright. But if I take this thing here, you can see the dots. You can see dots over here. See these dots? See the dots there? Those bright dots are the distance between those dots is delta Y. Okay? And the distance from the distance from the slide here and the screen, which is the Cadillac, is going to be L. Trying to get this so you can see the dots better. I think they're pretty clear there. You see the principal center dot is so bright it's washed out, but there's a dot to the right of it. So there's this dot. There's this dot to the right of it, a dot to the right of that. And so it's the distance between those bright dots that we're looking at. Now if I reduce L, the distance between the dots gets closer together. So you can see that happening. See those dots getting closer together? Yeah. And then bring it back here. The dots get further apart. See, the dots get further apart there. If I move it in, the dots get closer. Moving it in, the dots get closer. Pulling it out, making L bigger, the dots get further away. Now, in order to see the dependence on D, the distance between the slits, you can look at this grating here, which has 1,000 lines. So you'll see here the dots are even further apart. See how far apart they are? So this is 1,000 lines per millimeter. You can see the dots are far apart. And then if I go to 500 lines per millimeter, see the dots are closer together. So this is 500 lines per millimeter. 1,000 lines per millimeter, the dots are further apart. In fact, they're twice as far apart, those diffraction spot maximums. Okay? Alright, so the next thing I want to do is I'll take my laser and turn it this way toward that. You see my laser beam. It's going to go over along parallel to the Cadillac, and it's going to hit this dresser over here. And this is the beam hitting right here. See my fingers pointing toward it. Okay. So what I'm going to do is I'm going to take different patterns of like double slits and single slits and look at the spray of maximums over there on that dresser. Now the distance L is the distance from the laser all the way to where the light is hitting that wooden dresser. Actually, it was a dresser I used when I was a little kid. It's a little desk. The front of it bends down and you can write on it. I'll show it to you. Right now it's just a little storage desk for all kinds of crud in the garage here. So if you lower this, you can see this sits like so, and you can hitch a chair up under that ledge and use that as a desk to write on. And you can put all your little pencils and things up here. I'm using it for like gardening stuff right now. This here is some tomato food, see? Here's some other liquid feed for your plants. Weed and grass herbicide. liquid plant food. See, all these things you get to do when you become a gardener. Okay, so right now we're trying to fertilize the garden of your mind with knowledge, though. So let's come back. So the L in the formula is the distance from the laser, or actually from where I'll put the screen, to the diffraction grating or double slit or single slit grating over to that dresser. And that's, to be honest with you, that's about 3 meters for me. I'd say that's about 9 feet easy, 9.5 feet. It's about 3 meters. So here, this thing right here is a, this thing right here, I'll hold it up to the light. You'll be able to see it. It has a bunch of double slits in it, that first column. And it has some single slits in the middle there. It has a slit that gets progressively narrow. It has some single slits here. So I'll put different gratings on the laser, and you could look over there and look at the change in the pattern that's seen on the screen over there. And I'll try and hold this steady my best. Okay, so here's a single slit. That's not doing very good, is it? You're not going to be able to see that. So what we're going to do is we're going to go back to the, we're going to come back over here to the, we're going to use the Cadillac again. Okay, let's use the Cadillac again and pull this table over here. Get it a little further away. I think what I'll do is, instead of using the Cadillac, I'll use the garage door over there. That might be a little better. So let's put the laser over here. I think the Cadillac distance is a little too far. And then let's take this diffraction pattern slide, this black one, and put different patterns in front of the thing. So let's take this and use these. I've got double slits on that second column. The center column is all single slits. So let's put that in there. See what we see. There's some single slits. A single slit right there. And those bumps are a little too much glare for you to see those bumps. Let me try another one. There you go. Now, I don't know how well you can see those bumps. I just want to show you a single slit, really, because let me get this set up here again and try it again. Okay, there you go. Right there, you can start to see. Let me get my camera in focus again. Hang on. See the bumps in that one area here. Let me try it again one more time. Okay, right there. You can see bumps, right? See the bumps? A little difficult for me to hold my hand steady. I guess I showed you double slit and end slit. Let me see a double slit again right here. There's double slit. If you freeze the frame, you'll be able to zoom in on that. See double slit. Here is, let me try end slits here. Right there. You can see bumps. If you go past, there they are. See the bumps? They're dots. They're pretty close together, but you can see them. I could change what I'm doing here. So you saw single slit, then you see here's a double slit. Those are hard to see. They're very faint. Here, let me get you another double slit here. Having trouble here, guys. Hang on. That's a double slit. Those dots are harder to see. A little bit easier to see these. This one right here. You can see bumps there, I think. Yeah, right there. See those bumps? Those are bright dots. Yeah. Okay, so this video is really just a demonstration of interference. I think that the algebra in the this is my laser again. You can see the particles of dust here in the garage. What might be fun though, here, let's have a little fun. I mean, after all, physics isn't all work. You got to have fun when you're doing physics. So let me come over here and light up a cigar. Okay. And I'll blow some smoke. At the beam. So let's go over here. We'll shoot the beam again long ways in the garage at that dresser over there. And let's blow some smoke at the beam. Watch this. Hang on. I lit up a Cuban cigar here. Let me see if I can blow some smoke on that beam and see the beam better. There you go. Hey, see that beam now? With all that smoke on it? Let me stack that beam with smoke again for you. Watch this. Ready? Now I can really see that laser beam because